Hello everyone. This is a lesson on working the numbers of the Consumer Price Index. So in this lesson you're going to figure out how to take the Consumer Price Index data, which I've posted out there on Blackboard, or you can find on the web at www.bls.gov, and how to use those numbers to calculate the inflation rate across years and to adjust prices in history and so forth. So let's get started. The first kind of problem that you might see is to adjust a historical price to the present. So I found this old photo. It's pretty interesting. Look at this. So this is a photo. Here, let me get my face out of the way. This is a photo that was taken in 1948 of some soda shop someplace, and that young couple's probably your grandparents before they were ever married, having some date there. And if you look in the background, look at this. If we blow this thing up, you see this Coca-Cola sign back here. 5 cents for Coca-Cola in 1948. It's unbelievably cheap, right? 5 cents in 1948. But remember that 5 cents would go a long ways in 1948 compared to the year 2013. So what we want to do is we want to figure out, well, really, how much was 5 cents worth? What would be the inflation adjusted price for a Coca-Cola from 1948 up to the year 2013? And here's how you do that. You take the Consumer Price Index in the year 2013, and the whole year is not over yet, so what we have is the CPI up to June of 2013. Alright, so let's start over. You take the price, which was 5 cents, 0.05, you multiply that price by the Consumer Price Index in 2013, which was 233.5, and you divide that by the Consumer Price Index for 1948, which was 24.1, and that gives me an answer of 48.4 cents, or in other words, something that cost 5 cents in 1948 adjusted for general inflation across all those years should cost 48.4 cents today. Now that seems really cheap, because I think Cokes are at least $1, maybe even $2 some places now. So we could interpret this to mean that the price of Coca-Cola has risen faster than the inflation rate since 1948, but be very careful with your interpretation, because remember, in 1948 Coca-Cola probably came in a bottle, and it would be only 6 ounces. In those days Cokes are really small, 6 ounces, where nowadays even a 12-ounce Coke is kind of considered a tiny one. So to really adjust it for the quality change that's occurred since 1948, you should probably multiply that 48 cents by at least 2 to get it up to 12 ounces, which would be about $1. And even at $1, it seems a little cheap to me, but maybe not. So I think it would be safe to interpret this to mean that the price of Coke has risen somewhat faster than the inflation rate, but probably not as dramatic as our analysis has shown. Okay, so that's the first kind of problem, adjusting a historical price to the present. One more time now, you take the price, you multiply it by the Consumer Price Index in the present, and then you divide that by the Consumer Price Index in the past, where your data came from, and you multiply the whole mess by 100 to get it into percent. Okay, the second kind of problem that you might need to do is to calculate the inflation rate between 2 consecutive years. So here's how you do that. All you do is you just calculate the percentage change in the Consumer Price Index from one year to the next. I see I've already done it here. Let me get that out. Alright, so let's just try it, and this is how you would do it. It would be the difference in the Consumer Price Index, say in 2012, and the year before. Alright, so there's the difference, and you would divide by the Consumer Price Index in the first year, which would be 2011, and you multiply that whole mess by 100, and there you go. The inflation rate for 2012 was 2.1%. The inflation rate for 2011 would be the difference in the CPI in 2011 and in 2010, and then divide it by the CPI in 2010, multiply the whole mess by 100. So if you take this and you just kind of figure the inflation rate for many years, you can kind of see that in recent history the Consumer Price Index has been about 2 or 3% a year, But look at this. Oh my gosh, if you go back to the early 80s, and I was alive then, I remember these days, the inflation rate was quite large and people were talking about inflation all the time and people were very, very worried. Then another interesting time is if you look at the American Civil War, that would be in the early 1860s. Remember, the federal government funded the war by printing more money, and so you had this tremendous inflation during those war years, and then when the war was over they stopped doing it and prices began to fall again. So this table that I've put out there on Blackboard is really useful, and you should spend some time working these numbers. In fact, you should call your grandparents or that old uncle or aunt and ask them to tell you about what prices were back in the day, and then you can use this index to adjust them to see how it compares to prices that you see. Alright, so then the next kind of problem that you might see is to calculate the average inflation rate across many years. So for example, I might ask you, well, what's been the average inflation rate, say from 2010 back to the year 2000, or from 2000 to 1990? So most students will first try it this way. They will calculate the inflation rate for each of those years, see it right here, and then they will just divide by how many they have. Now that will get you close to the answer, but it won't be exactly correct. That's called an arithmetic mean, and an arithmetic mean is inappropriate here because there's compounding going on. In other words, any inflation that's showing up here in 2001 is then used to calculate the inflation rate for 2002, and that result is then used to calculate the inflation rate in 2003, and so forth. There's compounding going on. So the only way to calculate the average inflation rate across a span of years, say from 2010 back to 2000, is to use a compounding formula, and I've generated one here. This is the one I want you to use. So if you haven't seen this formula before, the way you read it is that the future value of something is equal to its present value. So this is the future value of something is equal to its present value times 1 plus the growth rate, that's the growth rate, raised to the number of years out that it is. So if we were going to calculate the average inflation rate from, say, the year 2010 down to 2000, it would be like this. The consumer price index in 2010 was 218.1, and the consumer price index in the year 2000 was 172.5 times 1 plus the growth rate, and that's the thing we're trying to figure out, times the number of years. Now the years is kind of tricky, so make sure you count it right. Let's see, from 2000 to 2010 would be exactly 10 years. Sometimes students will say that's 11 years because they will begin counting with the year 2000. But remember, the first year of inflation would be from the year 2000 to 2001. So it takes 2 years to get the first one, and then another year after that. So from 2000 to 2010 would be 10 years out. Okay, so the first thing I would do to solve this simple problem is I would divide both sides by 172.5, and that gives me 1.2643 equals 1 plus the growth rate raised to the number of years out. Now the next thing I need to do is to take the 10th root of both sides. So some of you whose algebra is a little bit weak, you might remember that if you had something simple, say like x squared equals 4, and you wanted to find out what x was, you would just take the square root of both sides, right? And you would write it like this, and you would get x equals 2. But in this particular problem, we have the 10th root. You see that? So we need to take the 10th root of both sides, and normally the way I notate that is I usually notate it like this. It's just another way of writing a root, right? So I'm going to take the 10th root of both sides, which my calculator can do, and I get the 10th root of this thing is 1.0237, and then on the right hand side all that's left is 1 plus the growth rate, and then if I subtract 1 from both sides, I get the growth rate is 0.0237, or if I wanted to put it in percent, it would be 2.37%. So that's the average inflation rate across those years, 2.37%. Now if you want to, you can shut this video down for a while and try to do it the way that seems easier. That is, take all the inflation rates and add them all up and divide by how many you had, and you should get a number very close to that, but not exactly that. So this is the correct answer, and that's the answer that I would expect on an exam. The next kind of problem that I might ask you is predicting the future price. Let's imagine something costs $5 today, and you were wondering what it would cost, say, in 10 years. The thing costs $5 today, and then we need some assumption about what the inflation rate will be out into the future. Let's make up some assumption that the inflation rate in the future is going to be, say, 6%, 0.06, and we want to know how much that $5 item would cost, say, in 10 years. You would do it like this, and that would be its future value. See how you set that up? So 1.06 raised to the 10th power gives me this, $5 times 1.7908, all right? And then multiplying those two things together, I get 8.95. Or the way you interpret this is something that costs $5 today, if the inflation rate in the future is 6%, that same thing will cost $8.95 in 10 years. All right? Then the next kind of problem is the hardest one. I left it for last, and that is how many years before prices double or prices triple. And to answer that, you need to use logs. See those rules of logs over there on the side? I didn't write them there just for nothing. You're going to need them here. So here's how this works. Again, this is your setup equation. All right. So suppose you wanted to know how long before things doubled in price. So start with a simple price, say like $1, and then you're going to multiply by 1 plus the growth rate. Now we need some assumption about what the inflation rate will be in the future. Let's just assume it's going to be something like maybe 5%. So if we have 5% inflation in the future, we want to know how many years before prices double, which would make its future value 2. Right? Something that costs $1 in the present is going to cost $2 when prices double. Now the reason this one's hard is because the thing you're trying to solve for is up there in an exponent. And to solve this kind of equation, you need to use this rule of logarithms. There's a rule of logarithms that says if you take the log of something raised to a power, you can bring the power outside, and it'll just be b times the log of a. So that's exactly the rule we're going to use here. So I'm going to rewrite this as the log of 2 equals the log of, I don't need the 1, right? The log of 1.05 raised to the number of years out. Then I'm going to apply this rule of logarithms, so it would be the log of 2 is equal to year times the log of 1.05. And I know that looks really hard, but actually those things are easily found in your calculator. The log of 2 divided by the log of 1.05 equals the year. And when I put that in my calculator, I get 14.206 years. So the way you read that is, if the inflation rate is 5%, prices will double in exactly 14.206 years. Alright, so that's the last kind of problem that I might ask you, and you should really work all these in practice. You'll find sample questions on old tests, and again, I hope you found this helpful. Good luck.